This is our world now. The world of the electron and the switch, the beauty of the baud. We exist without nationality, skin color, or religious bias. You wage wars, murder, cheat, lie to us and try to make us believe it's for our own good, yet we're the criminals. Yes, I am a criminal. My crime is that of curiosity. I am a hacker, and this is my manifesto. Huh? Right? Manifesto? You may stop me, but you can't stop us all.
Oh, that's cool.
Cool? Cool. You think it's cool?
It's cool.
It's not cool. It's commie bullshit.
Hello, good morning, everybody. Yeah, clip from Hackers, one of the all-time worst, most over-the-top movies ever. But it has continued to have a real reach into hacker culture and inspire people. And this also continues my tradition of starting my Penn State talk with a stupid movie clip. Whether it's Independence Day, or The Net, or Jurassic Park. Anyway, hi, I'm Ed Marczak. And I don't know if you have your mic on. Tom Burgin. And we're going to talk a little bit about reverse engineering today. One thing I always do for my talks is I have a doc with a link to everything that we talk about, so you don't have to worry about scribbling it down really, really fast. So I'll leave that up there for a second. You can look at the doc. You don't have to worry about if you miss it on a slide. This is a fairly technical session, so it's a no BS session, maybe a little BS. This is also a link, and you'll find it in that doc as well. For those of you who would like to follow along with one portion of this, this is a binary that you can disassemble with LLDB while we're doing it. You will need Xcode for that. If you don't have Xcode on your machine already, sorry. There's no possible way you can download and install Xcode before this session is over. Before we go on, I definitely want to thank all the people at Penn State, particularly the very visible people, Rusty, Justin, Gretchen, other Justin, and Dave Test, who I see is running around taking pictures, esteemed board members, everyone at Penn State, the staff putting all this together. So I think we should give them a big round of applause, because they're the best. They're doing a great job. And I see Justin sitting there in the back. They're the best. Like, you could ask them anything. They know it off the top of their head. What session's in here next? Boom. How many speakers total at the conference? 75. Damn. Anything. They're the best. So thank you. Thank you and the staff. So what are we doing here today? You might have thought I was Greg Nagel. That's Dean Hall 2. I'll give you a second if you want to. I won't even look. If you're in the wrong session, you can go. No shame. All right. Everyone's stayed. That's good. So we're going to talk a little bit about reverse engineering. You could probably have a class for a week or a month on reverse engineering and not cover everything. So this is just going to be, you've never really touched it before. We want to introduce you to it. You might be inspired different ways. I know I had been. You might have been inspired from a book. One of my favorites, Cuckoo's Egg. If you've never read it, certainly go read it. The technology's a bit dated, but it's still a fun read about a sysadmin who finds a hacker on his network and how he sort of roots him out. Could be a movie. Ghost in the Shell, standalone complex, also one of my favorites. If you're not familiar with it, takes place in the future. People are sort of cyborgs. The case of the Laughing Man is where this one hacker is so good, when he's committing a crime, he can hack people's eyes so they see this symbol, and of course, now no one knows the crime is going on, basically, or they can't see who's committing it. Or it could be something like Hackers. You need your eyepiece to do your hacking and silly over-the-top stuff. If we're going to talk about reverse engineering, we need to talk a little bit about computer science. So this is going to be the fastest computer science overview ever. Computer science is responsible for a lot of the things we do in the modern world. One of the hot topics now is machine learning. Google's Translate app, you point a camera at something and it translates it in real time. Although I ran into this ATM that was in Spanish, so I used my Google Translate app, and it doesn't always do a perfect job in its learning. Enter its secret key, and I love that OK was translated to this well. And sometimes it makes other mistakes, like press cancer if wrong. You might want a fast 100 of checks. But in general, machine learning does, a good job. But we're not getting up to that level of computer science. What we're going to talk about right now is architecture. When you're talking about architecture, you're really just talking about the chip, the CPU of the machine you're on. And today, what we talk about is going to be applicable to a wide range of chips, but we're going to specifically be talking about x86, the crappiest of architectures. It's what's in your Mac, x86. We're not really going to be focusing on ARM, which powers all your iOS devices. A lot of this stuff is still applicable. Like I know we're going to be talking about Hopper a little bit later. Hopper does ARM disassembly, which is what your iOS device uses. You can do that offline, but we're going to be focusing on x86. What a CPU does, you might have heard of this term, IPO, input, process, output. That's all a CPU does. Whether you're playing a game or looking at a spreadsheet or whatever, takes some input, processes it, outputs it into storage or on disk or something else. And it does this mainly through a piece on the CPU called the ALU, the Arithmetic Logic Unit. And it takes an operator, it takes some operands, which is what the operator is operating on, and it gives you some output. So for example, the operand might be addition, and you get some numbers, 3 and 5, and it processes them, and it gets 8, and it outputs it. So that's just a little piece of the CPU. A CPU also has registers. Registers are just a fancy name for memory that is directly on the CPU itself. But what's important about a register is that because it's directly built into the CPU, it's the fastest memory access possible. So you will, when you're reverse engineering something, you'll see the CPU using registers all the time, and you will become familiar with their names. In our fictional CPU here, we have 8 registers named AX, BX, CX, DX, SI, DI, BP, and SP. CPU will have to do some input and output. So it'll have an I/O bus, and that I/O bus is usually connected to main storage, main RAM somehow. And of course, your main RAM is numbered from 0 all the way up through however much RAM you have, 4 gig, 8 gig, whatever. And here's a fictional assembly language program. The assembly language command move. We're going to move the literal number 76 into the AX register. The next line says we're going to add 1 to whatever's in AX and store it in BX. And the third line says we're going to take that result in BX and move it to memory location 1000. So hopefully that's storage that's allocated to our program. We're going to push that value in there. So you can see assembly language instructions when you're reverse engineering. Assembly language instructions are very, very, very specific. So if you write a line of code in C or Objective-C or Swift, that one line, when you disassemble it, usually translates to 5, 10 assembly language instructions. Here's a little bit more complex assembly example. It's a loop. So we're going to move 12 into the AX register. And you can think of these register names just as variable names. So this is like saying AX equals 12. We're going to have a label called begin. We're going to add 1 to whatever's in AX. We're going to compare whatever's in AX to 24. And the next line says, if that's equal to 24, jump if equal to memory location 300. And hopefully sitting at memory location 300 is code that we want to run. Otherwise, you might crash. If it's not equal, it falls through the next line, and it says jump to that label begin. So you have this nice loop that will run until AX is 24, and then it'll jump out. Of course, all those assembly language instructions are for us humans. They're called mnemonics. What the computer really deals with are binary numbers, 1s and 0s, that's it. So each of these mnemonics, really, the computer sees a number. So this is a very short list, but in our fictional assembly instruction set. Add is 0, subtract is 1, move is 2, it's not 10, it's binary. Move is 2, and test is 3. And of course, the registers are all numeric. So 0, 1, 2, 3, 4, AX, BX, CX, and DX. So really, when the computer is moving through all this, it's seeing something like this. Here's our move instruction, here's 12, and we're moving 12 into the AX register. It's sort of a simplified version of what the computer's doing all the time. So yeah, why is this important? Games, of course. One of my favorites, TIS 100. Has anyone played TIS 100? Yeah. If you haven't played TIS 100, it gives you a fictional CPU that you program through assembly language. So it's the assembly language game you never knew you wanted. It's really great, and I have to say it does a really great job of giving you this very stripped down instruction set, and you solve puzzles using them. You come out feeling like you have a pretty good grasp of assembly language. Else heart.break, if anyone's seen this. It's not assembly language, but everything in the universe of this game is code, so you can walk up to anything and reprogram it, which is pretty cool. And more recently, Human Resource Machine, if anyone's seen this. It's on the Mac, it's on iOS. And this is one of those games that you feel like you're playing a game, but before you know it, you're like, damn it, they taught me something. And they basically teach you, to go and fill these boxes and do these jobs, and before you know it, you have a little program. So these are some good resources to learn programming, I think, in sort of the form of a game. All right. So now we have this computer, we have the CPU, and you boot up this computer, and you have this big chunk of memory. So here's our big chunk of memory, 0 through 4 gig, right, let's say. And so that's 0 through FFFFFFFF. And you boot up your computer, and what happens? Starts populating this RAM. Down at the low end of RAM are things for the computer to maintain itself and the OS to maintain itself. You don't get to touch that. That's not for you. If you ever want to write a program that crashes on purpose, and you might want to do that, I've done that in the past, try to write to memory location 0, boom, crash. So yeah, the low RAM, not for you. Then the OS itself starts loading into RAM. OS itself, I think even in Windows and Linux, the OS goes way up top. OS 10 puts itself in high RAM. So now you have this big chunk right in the middle of accessible free RAM. But we're not done yet, because the OS needs to set up some data structures to manage itself. And it sets up a stack and a heap. And these are two data structures that you learned about in computer science. The stack grows down in RAM, and the heap grows up. So as you add things to the stack, it grows down in memory. And as you add things to the heap, it grows up, squeezing that accessible RAM. So now your OS is booted, and you run a program. Let's take a look at what a program looks like, which would load itself somewhere in this accessible RAM. And it turns out a program looks pretty much like a replica of what the system itself does. Down bottom, you get a data and a text segment. That's the program itself. You don't get to fool around with that memory. It sets up a stack up top and a heap down bottom. And it reserves a little space in the middle, so as it makes memory allocations, it has some place to put all these things. And just like before, the stack grows down, the heap grows up. Anyone remember classic Mac OS? Yeah, and you got to set how much RAM a program could take up. And if you set this too low, you could get a stack heap collision. They would grow into each other and the program would crash. Nowadays, you pretty much never get that, because paging out and virtual memory and things like that almost guarantee, if you're a programmer and you ask for memory, you get it. But back in the day, classic OS, you could run out of RAM pretty quickly. But what else was classic OS really good for? Hacking your school's computer systems, of course.
What's up? Oh my god. Oh my god.
All right, now that we got some inspiration for hacking, we're going to dig into a simple C program. And we're going to look in particular about how the stack works with this C program. So we have a simple C program, main and add are our two functions. In the end, it essentially adds 4 and 5 and prints it out. Pretty simple. So let's look at in LLDB what a backtrace looks like. This is the stack. The stack is a first in, last out data structure. It grows down in memory. Things are stacked on like dinner plates and popped off the stack as they're not needed anymore. So we see if we go ahead and break inside the add function. At the bottom of the stack, we have our dynamic loader. The OS is getting ready to call our program. Then on top of that, we have main, and then on top of that, we have add. And as add does its addition and returns its value, it's popped off the stack. As main goes ahead and prints out and exits, it's popped off the stack, and the dynamic loader eventually goes as well. There it is. So if we wanted to essentially call another function from add, what would that look like in the stack? Just adds right on top of add. So we have our fuzzit function that we're calling from add, and we can see that it is pushed right on top of the stack, and as whatever fuzzit does returns, it'll pop off all the way down the line. So how do we actually get 4 and 5, those integers, from main to add? Calling conventions. That's what we're going to talk about. Essentially, it's an agreement. It's a way that the compiler goes ahead and agrees upon all the functions are going to do this, and this is the way that we're going to pass variables around. This is the way that we're going to return values. And to do that, we're going to talk about some registers. We have our general purpose registers, our AX, BX, CX, and DX. You can access the high and low bit of AX, so you can get the 8-bit chunks of AX with the AH and AL. We have specific registers. This keeps track of where we are in our program, the instruction pointer. Our base pointer, BP, tells us where the top of our stack is, and the stack pointer shows us where the bottom of our stack is. And we'll see that grow down in memory in our example in a little bit. We also have flags. They're set after each instruction. They can, your 0 flag can be set to 0 if your instruction resulted in 0. You can have integer overflow flags if you try to cram too big of a number in your register. So flags are handy for optimization and other types of things that you need to check after your instructions go. So our architecture, we have nowadays 32-bit, 64-bit. Back in the day, we had 16-bit registers. That's what our AX is. It's a 16-bit register. A little later on, we got the extended EAX registers, and that's 32-bit, so we can put a 32-bit number in there. And on our modern day Macs, most of them are running 64-bit and chips, and we have the REX registers, which we can hold 64-bit numbers in. So going back to the calling conventions, how do we get that 4 and 5 from main into add? Well, we have these registers, the DI, SI, DX, CX, R8, and R9. Those are the first 6 integer registers that you'll use to pass along integers from function to function. So when we disassemble our program, we should see DI and SI being used to populate 4 and 5, and then we call our add function, and then the add function knows that, okay, DI and SI are the first 2 registers that will populate these integers, and we'll go ahead and use those to do our work. The XMM registers are for floating point numbers, so numbers that are non-integers. With x86, we have this notion of call save, which essentially means, in our example, the add function is going to be responsible for setting up its own stack. So it's going to take the current base pointer of the stack, save it, and then go ahead and set our new stack pointer to that base pointer. And we'll see that as a dead giveaway at the beginning of every function that we disassemble. And then when the function's ready to return, we have the RAX return value. And this, by convention, will be used, and we'll see it clear as day at the end of every function. If it's returning an integer, we'll put it in the AX type register, and then the main program knows where to go ahead and get that return value.
Yeah, did anyone watch the WDC video for debugging? The WDC presenter, at some point sort of mentioned, he's like, well, and I know the return value is in the AX register, and I just know that. And I think people
They're like,
sitting in there,
why do you
wow,
know that?
How do you know that? He's a magician. Like, no, that's
it's
just the way
convention.
it works. It's convention. So if a function's returning something, it's going to stick it in the AX register.
Exactly. So to get ready to examine code, we obviously have to watch another video.
There's a new virus in the database.
What's happening?
It's replicating, eating up memory. What do I do?
Type cookie, you idiot. I'll head him off at the pass.
We have a zero bug attacking all login and overlay files.
Run antivirus. Give me a systems display. Die, dickweeds.
The rabbit is in the administration system.
Send a flu shot.
Rabbit, flu shot, someone talk to me.
It's so bad, it's so good. So yeah, okay, so now let's sort of get to the heart of all of this. Examining code or reverse engineering. Also, because we live in the world of Twitter, you will often see reverse engineering abbreviated down to RE, not regular expressions, but reverse engineering. And I think this reverse engineering kind of falls into two classes of things. So what are they? Static analysis and dynamic analysis. And we're going to look at the first one first, static analysis. This is sort of the dead rat sitting on the table, and you get to poke it and see what it was, what it was doing maybe, and what you can ascertain about it. This is like looking at a binary on disk. It's not running, it's not moving. You get to kind of go through it. And the first disclaimer I want to make while we're talking about this is check yourself before you wreck yourself, because malware is bad for your health. If you are reverse engineering a binary that you do not know where it came from, or you suspect it is malware or something unwanted, please do your reverse engineering in a VM at the very least. I have definitely done this. I'm guilty of this, where you're stepping through code and you hit next and you just go, damn it, it just installed something on my system. And it feels terrible. It just feels dirty. So yes, feel free to do your reverse engineering inside a VM. The first tool that's sort of useful that I want to mention is called OTool, and you will need Xcode. It comes with Xcode, and what OTool does, let's look at our stack trace program that Tom was showing us before. OTool, with the parameters T and V. T means you want to get the text segment, and that's where your program is located, and V just means be verbose. And we're going to look at this stack trace program. And it gives you this nice disassembly of your program. Here's the add function and the disassembly of it, and the main function and the disassembly of it. And as Tom was mentioning, this is one of those dead giveaways. Beginning of every function, the function that gets called needs to go set up the stack. So it's going to push the base pointer, RBP, and it's going to move the stack pointer to become the new base pointer. So dead giveaway, beginning of every function. Even main has this same sort of thing. So that's OTool, sort of useful, sort of a quick and dirty way to look at a program. Slightly better is if you're dealing with Objective-C code. There's this tool that rides on top of OTool, gives you much better output, called ClassDump. ClassDump is not an Apple tool. It does not come with Xcode. It can be found at that URL right there. And like I said, it's very specific to Objective-C programs. Fortunately, there are still a lot of Objective-C programs out there. So if we run class dump on our stack trace program, which is straight C, you'll see it gives us this message down here that says, this file does not contain any Objective-C runtime information. But if we run class dump on something like tweetbot, for example, and pipe it to less, you'll see it gives us all sorts of great information. Right? It gives us structures, variables. If you go further down, it gives method names. This is a huge resource when you're reverse engineering to kind of understand what the program is doing without even disassembling anything. So it'll give you locations to go target. So if you know you're reverse engineering a program and you're specifically interested in this one thing, how does it do this one thing? Like if you're interested in how tweetbot does a certain animation, well, I would go through here and look for animate, right? And oh, hey, look at this. There are a bunch of methods that talk about animating things. So huge advantage. Again, only works with Objective-C programs. Strings. Strings, handy. Comes built in to the OS. And if we run our stack trace program, you already saw the source code. But if we run it, you'll see it prints this out. The sum is 9. That's all this program does, add 4 and 5. If we run strings, God, come on our stack trace program, it strips out all the binary gunk, things that don't look human readable, and it only gives us things that look human readable. So again, not the most comprehensive tool in the world, but it gives you sort of this little advantage on seeing what a program might print out, what its human readable strings are. Something else you might want to know about strings, 2 reasons you should actually redirect a program into strings. I started using this method a while ago back in the days of fat binaries. If you just ran strings and passed it in the program, it would only give you the first architecture that it found. If you redirected it, it gives you all the architectures. The other thing that this does is it gives you a little bit more information. It gives you all the text segments, and also Tavis. Anyone know Tavis O from the security world? He finds holes in all these things. He had this post probably within the last year, and he says, you know, how many people pass arbitrary things to strings? Which a lot of people do. And he said, yeah, don't do that, because I have this 0 day in strings that if I have you pass the right things to strings, I can take over your computer. So that's subverted by not using the program as input, but redirecting something in. So fun. XXD, it's a built-in hex viewer. So if we XXD our stack trace sample program, you'll see it gives us this hex dump of it. A lot of times looking at something in a hex dump, if I can get back to it, is a little bit more useful. I would say if you were ever reversing a file on disk, like a data file, very useful to look at through a hex viewer. So know that you have XXD built in. You know, you can use that via SSH, of course, because it's built in. But if you're doing something on your local machine, one of my favorites is Hex Fiend, written by Peter Amon, who's also known as Ridiculous Fish. He is ridiculously bright. Hex Fiend is this masterpiece of computer science, and Apple even thought so. So if you go to About Xcode, you'll find this little credit to Peter Amon, because Apple used Hex Fiend inside of Xcode. Anytime you see hex dumps in Xcode, it's Hex Fiend. So yeah, that's pretty cool. And his website, I don't think he's blogged in a while, but even his old blog posts are like these mind-blowing reads of reverse engineering and how your computer works. So ridiculousfish.com. So let's take our same program and load it up in Hex Fiend. So you get this nice GUI, stretch this out, and of course this is a recent for me because I've been practicing. And the good thing about Hex Fiend is, unlike XXD, I wish I could stretch this out more, but I don't know what I'm doing apparently. There we go. Is that this isn't only a hex viewer, but it's a hex editor. So let's take a quick look. Let's go back to our stack trace program. Stack trace, we run it. It says the sum is 9. We already have the source code. We could just recompile it if we want to. But we know what it's doing. It's adding two numbers, 4 and 5. So this is one of those things that I think the more you do it, the more you get used to it. But here you can see these program segments, page 0, text, stubs. And if you start looking through this program, you get used to seeing this, like a bunch of space and then this binary looking garbage. But we know this is part of our program because we see here it says the sum is %d. So this is part of our program, and we can just go off and edit this. So after looking at this, I already know, but Hex Fiend has this nice find function that you can use for searching. So let's take this. Here's B8, and this is just setting up, this is assigning a variable with 4. B9, this is just another variable, and it's assigning it 5. Let's delete that and make this 9. Why not? And if I save that, and we come back and run our stack trace program, it tells us the sum is 13, because we added 9 and 4 instead. So that's pretty cool. Something I should have mentioned a little earlier is that on 10.11, SIP will prevent you from doing a lot of this. SIP will prevent you from attaching to Apple binaries, the OS stuff. It'll prevent you from editing this stuff on disk. What's that? And the dynamic loader. And yeah, it keeps you away from the dynamic loader, which might not be that big of a deal, but it can be confusing if you think you're going to go off and debug the dynamic loader. So yeah, if this is another reason to maybe run something in a VM, because you can just turn SIP off and then go debug and poke at anything that you like. So yeah, SIP. I know most developers I know just turn SIP off. So here we are with the other method, dynamic analysis. It's the live mouse running through the maze, and you can sort of watch it in action and figure out what it's going to do. First thing I'm going to mention is Xcode. And when you're using Xcode, you have access to the source. So I wouldn't call it reverse engineering, but as you're getting into this and as you're learning about this, go get a project off of GitHub, load it into Xcode, and step through it in the debugger. It's a great way to get used to the flow of debugging, knowing what you're seeing. As I mentioned, the more you do this, the more you get familiar with patterns, and you see these things, and when you're reverse engineering something that you're not familiar with, you can kind of go, aha, I've seen that before. I know what this is doing. So Xcode is a good tool for this. It's free, et cetera, but it's not really reverse engineering. The first one that you probably have heard about is LLDB, and this does come with Xcode, so you'll need Xcode to get LLDB. And let's take a look at our stack trace program in LLDB. So LLDB can load a program off disk and start executing it. LLDB can also attach to an already running process, and you just look up the process ID and you say LLDB-P and give it the process ID, and it'll attach to something already running, and you can start stepping through that. We're not going to do that right now. We're going to look at stack trace. So if you are following along, you will not have this line. This is something we're going to talk about a little later. But you can see LLDB does give you this message, target create stack trace, current executable step to stack trace, and it tells you the architecture that it's loading it for. First thing I'm going to do is I'm going to put a breakpoint on our main function. You can shorten the word breakpoint right down to B, so I'm going to do that. Break on main. And when I hit enter, it tells me breakpoint 1 is set, where main address, and it gives you the address that it sets the breakpoint on. Breakpoints in LLDB are really cool, especially if you're reverse engineering something you don't know about. You can tell it to set breakpoints and give it a regular expression. So again, back to my tweetbot example. Let's say you were trying to figure out something on how it animates something. You can go set a breakpoint on any method name that has animate in it. So very, very powerful. And then now that we have this breakpoint set, I'm just going to type run. And here we are. And it tells us right away, process stopped. Why did it stop? Here's the reason. We hit our breakpoint. It's not because it crashed. We hit our breakpoint. And it gives you 4 lines of disassembly. And it puts an arrow right next to the next instruction it's going to execute. And some other debuggers make this a little bit more clear, but that's the register IP. That's the instruction pointer. It's pointing to the next instruction that's going to execute. And as we've mentioned a few times, here's this setup. Why does main need to do this setup? Who's calling main? Well, the dynamic loader. So we don't see that here. We're getting right into our program, but even main is called by something else. It's called by the dynamic loader. So it has to do the same thing any other function does and set up the stack. So it's pushing the base pointer, it's moving the new stack pointer to be the base pointer. So the command you'll probably use most in LLDB is next, shortened down to N. So I'm just going to type N and hit return, and here we go. We're at the next instruction, which we already know was the move instruction. And just for those of you who might be curious, the Q in this move command is for quad word, which means it's a 64-bit value. You'll see down here we have move L. That's a long value. That's the difference between move Q and move L. So they, like with the register names that kept expanding as we got into 64-bit computers in 32 and 64, they had to keep renaming commands to be specific about what those commands were doing. Next. Now, this command might look strange. We're going to subtract Q, quad word. We're going to subtract 32, because we're in hex. That's not 20. We're going to subtract 32 from the stack pointer. So that gives us 32 bytes on our stack. Since this is a nice small program, 32 bytes is plenty. And then this is like setting up variables. Again, you can think of these register names almost as variables. Here we're saying EAX is equal to 4, right? So we're moving 4 into the EAX register. We know that because we've seen the source code. We know what we're doing here. We're assigning 4. And now because I changed it on disk, it's actually 9, not 5 anymore. If you were following along, your binary probably says 5 here. Unless you followed along with the Hex Fiend example. If so, hey, right on. And we're moving 9 into ECX. That's just assigning variables. The other thing I should point out is this program was compiled without any optimizations. So there are some things, as we're reversing it, you'll say, wow, that was a lot of steps for that. Why is it so verbose? Well, if we optimized this, it might do something a lot smarter, like moving things directly from one register to another rather than move it, store it, move it back. So this is a little simplified debugging exercise. And in this case, now we're going to move EDI into -4 off the stack. So again, the stack goes downward in memory, so we're subtracting 4 from the base pointer and storing whatever's in the EDI register right in there. And if you ever want to know what's in a register, there's a great command, register read. We can shorten these commands a little bit. Register read EDI, and you can see it's the number 1 in EDI. And you can do this with any register. Actually, you can just do register read R, and it'll show you all the registers. That's usually a lot more information than you care about. But you can see RAX, BXCX, etc. Next, we're back to our disassembly. We're moving RSI into 10 off the stack. We're moving 0. We're going to move EAX into EDI, move ECX into ESI.
Convention.
Yes, that's right. I'm sorry, I should have mentioned that. This is back to the calling conventions. We're setting up to call a function, so we're moving these values into the known places that this function is going to pick up those values from. The calling conventions are interesting because Windows, even though it runs on an x86, uses completely different calling conventions. So if you're ever disassembling a Windows program, a lot of it will look similar because they're x86 opcodes, but then it goes to call a function and you're like, what the heck is going on here? Linux and BSD running on x86 are much closer to what OS X does. And then here, the next spot, we have call. We're going to go off and call this function, which is our add function. And instead of typing n for next, which would just run that function and come back to me, I'm going to type s for step, which means we want to step into this function and follow the execution. So now it tells us we are in stack trace and the add function. And here we go again. We have to set up the stack. So we're going to push RBP. Next, we're going to move the current stack pointer to be the base pointer. And then we're going to take these values off of here. DI is going to go onto the stack. SI is going to go onto the stack. And this move 0 onto the stack, your compiler is putting that there for you. It's called a stack guard. And what most modern compilers do now is they put this known value at the end of the stack, and it will go and check for it. And if that ever is not there, it'll know the stack is corrupted, something's gone wrong, and it'll usually just crash your program. So when you're disassembling something and you see a 0 get moved onto the stack for no apparent reason, that's the reason. So then here we are taking these values from the stack, and we're going to do some operations on them. So we take this value off the stack and put it into ESI, and the next command, we're going to add this other value from the stack to ESI, and it just accumulates in ESI when we use add. Then we're going to take ESI and put it back on the stack. And then we're going to take this value from the stack and put it in EAX. Why? Conventions. Calling conventions. This is how we return values to main. We said this before. Anytime a function is going to return and it needs to return an integer value, it's going to put it in EAX. And we're going to do that right now. And then we're going to pop the stack back and return. Oops, what the hell did I do? Oh yeah, okay, sorry. So now this is prepping to go call printf. So we're loading this string. The sum is %d, return. And then we're moving these values into place. I'm just going to come down here to this call. And anytime you see this where you're calling a function like printf, instead of going and tracing this, I'm just going to type n because we don't want to debug printf. We don't really care about that. And you'll see after I type next, it calls printf and types the sum is 13. So once you get your answer when you're debugging, you can type C for continue and press return, and it'll just go off and continue. If you did have any other breakpoints, it would stop on those breakpoints, but I didn't. Interestingly, in Xcode 8, one of the things they announced at WDC was this batch mode for LLDB, which is actually really cool. So if your program crashes only every now and then, you can put LLDB in a loop, in like sort of a bash while loop, to go call LLDB and load your program. And if it exits cleanly, LLDB exits and then reloads it. But if it ever crashes, it stops and waits for you to go inspect things and look at the backtrace and figure out. Then you get to poke around. One thing I should have showed actually. That's kind of cool when you're debugging. I'm going to break on main again and run, and we'll just step through this till we're here. We're going to call add, and we'll step into it. Now we're in our add function. As Tom was mentioning before, when you're in LLDB, you can type BT for backtrace, and it'll show you where you are, how deep in the program you are. So Starting at the bottom, the dynamic loader loaded our program and called main. We went through the main function we called add. In LLDB, if you want to inspect something above you, so we're in add, but let's say we want to know something about main, where we came from. You can type up, and you can look at all the variables in the stack above you, and when you're done, you can type down, and you go back down into your program. And the other thing that I mentioned the other day when we were running through this, LLDB keeps getting better and better and better. I don't know if anyone's been playing with LLDB for as long as it's been out. Apple, about 3 years ago, when they introduced LLDB, gave this presentation at WDC that like people's jaws were dropping, like, oh, that's amazing. And then you went to try it on your own and none of it worked. It was terrible. But it's gotten better so quickly, which is great. I don't know when they added this, but they added this convenience for arguments that get passed on the stack. LLDB is smart enough to know the calling conventions and how it works. So you can print arg1. It knows that this is the first argument that got passed. So that's another like little shorthand that you can go look at. So our first argument is 4. You can do it for arg2, 9. So it's kind of smart enough to know this stuff. So that's a convenience that we didn't have back in the GDB days. So pretty cool. Continue, exit. Command D will get you out of that. Hopper. Anyone used Hopper in the past? Yeah, so if that LLDB stuff puts you off, there are other debuggers out there, and Hopper is one of them. Hopper is excellent. We love Hopper, and you can buy commercial tools. Hopper is a commercial tool, and you can find more about it at this URL. $89. Super affordable for what Hopper does. If you've looked at other commercial tools, they can run into the thousands of dollars. I mean, thousands and thousands of dollars. IDA Pro is probably the most notable. That probably at its base runs you $4,000, and then there's all these add-ons for it. So $89, I'm telling you, this is a steal. And Tom's going to lead us through some cool exercises in Hopper.
All right. So we're going to load up Hopper. We're going to keep beating on this dead horse of stack trace for a little bit, and then we'll get into some fun. So we're going to load up Hopper. If it's the first time you've launched Hopper, the first thing I always do is go to Preferences and turn off this Intel syntax. For some reason, Hopper has that on by default. Everything you've been seeing with LLDB has the AT&T syntax, so things will be reversed. So I usually uncheck that.
Yeah. Most tools default to AT&T syntax, and the fun thing about Intel syntax assembly and AT&T syntax assembly is that they're exactly backwards.
Yeah.
I don't know where the two standards came from, but yeah, sometimes you might be looking at assembly and not understand it. Make sure you're not looking at it in Intel syntax. Most tools, OTool, everything we've showed defaults to AT&T. So
Yeah, if you ever see a register thinking you're putting it onto a literal value, you're probably in Intel syntax. So we're going to go to File, Read Executable to Disassemble. And let's go to our stack trace program. And this gets us, sweet, a nice GUI, same stuff we were looking at in LLDB and other disassemblers. Oh, your reverse scrolling, Ed.
Natural scrolling. Natural. The right way.
Fair enough. So we have our add and our main functions. They're just assembled here for us. And what we're going to do, since we know these calling conventions, we're going to muck around with them a little bit and abuse them a little bit. So we know that coming in on EDI and ESI are two arguments, 4 and 9, I guess now they are. And we see that they're going to be put onto the stack here. This looks a little different, this var4. If you scroll on the side here, it will show you what they represent, -4, so -4 off the stack, -8 off the stack for the sizes of these integers. So let's go ahead and put a breakpoint. It's a nice, easy way to put a breakpoint. You don't have to type B and regular expressions. You can just go and find it and click on it in the gutter here. And Hopper has LLDB debugger with this nice GUI wrap around it right here built in. So we can see we have all of our play buttons, pause, step into, next, step out of, and all of our registers listed here. So let's go ahead and attach the program and play it. And we see here, oh, nice. All these registers are populated. They turn red when they change. And we'll see that in a second. We can see our stack right here. And we see right here the instruction pointer. This is the instruction we're about to execute. And we're going to move our EDI register, whatever's in there, to the stack. And we can see here the DI has 4 in it. So what we're going to do is we're going to actually take a look at the stack in memory, which is represented by our BP, our base pointer. So let's go to our base pointer. And since the stack grows downwards and Hopper puts lower memory addresses up, we're going to go ahead and scroll up just a little bit so we can see what's going to be populated. So right here is probably the 32 bytes-ish that were assigned to our stack. And if we click next, we should see 4 populate on this. Oh yeah, there it is, right there. I don't know if you saw that populate. So we're looking right now in memory at the stack, and there's our 4 value that just got popped on there, pushed on there. So what's cool about Hopper, it's also an editor. So we can edit live in memory that number, and let's set it to 255, and continue our program, and look at the output. Sweet. We passed in 4 and 5 to that function, but we got out, or 4 and 9, we got out 255 plus 9. So that's looking pretty cool, or whatever it was. Forget what number it was earlier. So that's all well and good, but what about an easier way to do it? Let's stop this. So we can come down here, since we know the convention that it's going to put a value into EAX before add returns. Let's go ahead and put a breakpoint there and run the program again. You can see we're about to execute this instruction that populates our value for EAX. And let's go ahead and step over that and see what it does. So we can see it puts in D, which is whatever that number is. I guess it's 13. And what we can do is abuse this. Before returning, we can just overwrite this register. So right here in the debug console, this is the same type of syntax. It's LLDB. So we can do reg read EAX. We can see it has the value there. But let's go ahead and we can do similar command, reg write EAX. And we're going to put in the literal value FF again. Failed to write. Not a valid unsigned integer value. Oh, I don't have to put the, that's for disassembling. Don't need the money sign. So if we read it now, it's FF255. So if we complete our program, sweet, we got back 255. So it's a way to, since we know the conventions, we can kind of abuse them live, which is kind of fun. But let's do something a little cooler. Let's load up this game. So one of our colleagues at Google wrote a snake game. It's like the old Nokia game where you had the snake go around and eat the items. I'm going to load up a version here.
I can't tell you how much productivity was lost over this game.
Welcome. So, you know, it's the standard game. You go around, you eat the fruit. Let me turn that down a little bit. And it gets faster as it goes along. Your snake gets longer. And it was a big deal. We all had to see who got the high score. A leaderboard was made. nightly revs of who had the highest score were sent out. It got pretty intense. So Ed figured, oh, he would just cheat, and he found a pretty good hack in the game where he would essentially not speed up every time he eats the fruit. So he got a pretty high score.
No LLDB, I'm telling you, comes in handy.
But once I started at Google, I was like, this can't do. I can't let Ed be the high scorer here. So I figured I wanted to find a way to get a perfect score. So we're going to go through that today. So we have the standard snake app in this read-only image. And let's go and load it up in Hopper. Hopper's really sweet because we can read this read-only application, modify it, but it's only modifying in Hopper. It's not actually writing back to the binary. So we can make it look like it's just normal. If someone were to launch that app, we haven't mucked with it. So this is an Objective-C program, so there's a lot of information here. We can see class names, method calls, same type of convention though, which is nice. So we're going to go through 3 hacks to get a perfect score. The first hack, Snake Hack 01, is we're going to switch every empty to give us a point. So every time the snake is moving along and doesn't hit anything, that'll give me a point, and that'll be pretty good. So let's try to do that. Looking through the code, we can see that there's an enum hit test result, and it's just full of an empty, a food, a wall, and a snake. And these are just 0, 1, 2, 3 when you actually look at it in disassembly. So what we want to do is essentially change the 1 where you hit the food, whatever you were going to call when you hit the 1, change that to whatever 0 is, which is empty. So we're just going to flip them. We're going to say when it's 0, do the food code. When it's 1, do the empty code. Or just no op for the 1 because we don't really need to do anything when the food happens. So let's go ahead and do that in Hopper. Not Keynote. All these things kind of look the same. So in this implementation, there's a method called tick game, and this fires multiple times a second to move your snake forward, see what area you're in, make sure you didn't hit the wall, and all it does is go through a case statement and says, did you hit the wall? No. Did you hit the snake? No. Did you hit the food? No. Whatever happens at that time. So if we scroll down here, we can see where that case statement starts. Right here. We can see our 1, and this is essentially 0, testing 0 EAX against EAX. So the first thing we want to do is change this, we're subtracting a long value from EAX, and if that's successful, we're going to jump to that you got a point code. So in Hopper, it's pretty cool. You can modify instructions. So if you go to the modify, you can go to assembly instruction, which is just option A, and we can retype a new instruction. So we're going to still do a sub L, but instead of 1, we're going to put a 0. And then that's going into the EAX register for testing. And boom, that took. And the next one we need to do is this test 0, and then the jump if equal and jump if not equal. We're just going to no-op these, which basically says do nothing, just skip over this little section. The way that this is compiled and the case statements go, if you do a 0 before a 1, it'll get confused and it'll crash. So we're just going to say, hey, ignore this, and we'll just look at 0s and not 1s. So let's see if that took. We're going to load up our debugger. We're going to run it with no breakpoints. All right, here's our game. Let's see what we got. Oh, good. So we do have continuous points for every empty square, but you can see, oh, it's getting faster. It's getting too fast. It's getting really hard to control. So obviously I couldn't get a perfect game with that, but I'm already getting a higher score than Ed was with his hack. There you go. Yeah, I know. Russell may be like, you got 300 points. Like, how's that happen?
See, the problem with this was Russell tried to have people not cheat. So after your game ended, it would take a screenshot of the thing, so you couldn't just poke a high score in there and have it upload. So
so you actually had to get this game score, and that would validate your points. So, okay, we can do better. Let's look at some other things that we can do. So let's look at our hack 2. And this is the hack that Ed found out of about. It's called the ink time multiplier. It's a constant floating point number embedded in the program. And it's set right now to 0.98. And that just multiplies 0.98 times your current speed for looping the game. And as you saw, it got faster and faster and faster the more points you got. So we just don't want to increase the speed, so we'll set it to 1.0. These are floating point numbers and how they look in the program. This is 0.98, doesn't look like it, but it is. And this is 1.0. So we're going to go and find ink time multiplier in our program and modify it to F03F. We can use the search on here and ink time multiplier. Oh, there it is. We can see it's a constant value because it just embeds the number right in the text of the program. Hopper itself has a hex editor, so Shift Command H will pull that up, and we can see that we have our hex view of our application. So we can see here 295C3F, that's what we wanted to mess with. So we're going to change it to F03F. So we're going to just zero this out, F0 and 3F. Okay, so that should make a 1.0 floating point number at that location. And the way this is compiled, there's two sections there. I'm not sure why that one's there, but it evaluates this one. So let's go ahead and run it again. And see if we still get our speed up. Sounds pretty constant. And actually, a funny story. You hear how the beeping stops every once in a while? My first bug at Google, these are the type of people that work at Google. My first bug was when I get 2 apples, I don't get 2 beeps. Like if an apple spawns, and it rarely happens, they spawn right next to each other. So that was my first bug to fix. Obviously, I'm not building off of that code. So, first fun day. All right, so that worked, but, well, let me run it again. You can see that it's a little hard to still get a perfect game because we start in the middle of the screen. It'd still be possible, but I would have to be really careful, and I just want a nice, easy way to cheat. So, I mean, I could come up here, but now I'm gonna have to do all these little things to get it. So I just want to, let's look at the third hack, but we want to start the snake down here so we can just follow along the edges and do a nice circle all the way out. So let's look at that third hack on how we should do that. And, oh, sweet. So within the new game method, Russell had coded using properties of this class, and there's a snake position property, and it sets it to the middle of the screen using floating point values. It's a NS point class, so it has an X and a Y using floating point numbers as them. So let's go and look in our program for these XMM registers, because we know floating point values go in the XMM registers. And we should be able to find where we need to modify.
We'll probably use up our 9 minutes. But
Still running? Quit that. Oops. Okay. So we're going to look for the new game method. And let's scroll down until we see some XMM registers and where it's setting those values for its initial setup. Ah, here they are. Right here and right here. So XMM0, XMM1, X and Y, that's essentially what it's setting, and it's going to assign them to the snake pos property to set the initial position of the snake. So we see it's taking some values and putting them, calculated values, and putting them in XMM0 and XMM1. Quickest way I know to just zero these out, so we want 0 and 0, the bottom left hand of the screen. We can just XOR the floating point number against itself, so it'll just check all the bits against each other, and if they're different, it gives you a 1, if they're the same, 0. And that will be a quick way, since they're the same, to get a 0, since we only have one instruction to work with. So let's change these to XOR a floating point number, XMM0 and XMM0. Copy this. Okay, cool. And we'll do the same thing for XMM1. And that should zero out both of these registers for the starting point of the game. And let's see if that took. All right, moment of truth. Sweet. So now we can have a nice, easy, lazy snake game, and we can try to get a perfect score. Now, remember that we no-opt out the section that was 1. So that means if we hit an apple, nothing's going to happen, and our snake will continue along its path, and there'll probably be like an empty square somewhere if the apple spawns right in front of us. It's only happened every once in a while that I've seen. Anyways, don't want to take up any more time with that, but it's possible to get a perfect game now, and I probably have the high score now at 138.
And also, if you thought you were going to fall asleep in this session, sorry, you picked the wrong one. Hey, thanks.
Yep.
All right, so I just want to mention some other tools. We don't have the time to go through them. The more and more you get into reverse engineering, the more and more tools you'll find, and the great thing about that is, just more things for your toolbox, different ways of looking at things and investigating. One of my favorites is called Voltron. It's made by a guy that you'll find calls himself Snare. He came up with some of the original Thunderstrike attacks against Macs, and he's always sort of digging into and reversing stuff. I see we have like 6 minutes left, so I'm not going to do a demo of this, but what it does, it's a Python program that lets you set up, this is using iTerm. If anyone uses the terminal a lot, like iTerm is fantastic. iTerm lets you split a single window into multiple terminals, and it works in conjunction with LLDB. And that's why I mentioned before, when I load LLDB, I get this little line that says Voltron loaded. And what it does is it lets you set up LLDB almost more like Hopper. So you still step through things with LLDB, but in these other panes, you can be looking at the stack or a nice big long disassembly listing. You can be looking at the backtrace. You can set up these panes to do almost whatever you want, which is really, really cool. Radar, if anyone's looked at this, they call this a reverse engineering framework. So it's not the same as LLDB. It has some really cool features. One of them is disassembling and showing output. I like this feature of Radar where it shows you the opcodes that the disassembly is using. The other cool feature of Radar is that if you're looking at a much larger program and as things call each other and branch and jump around, it will give you a graph for that, which is really cool. You can expand these boxes to show code, but once you're in a really large program, it's too much to show, and you can hit the tab key, hop around these sections of code, and it will show you the disassembly for the current module in the upper left-hand corner. And it's hard to see on this screen, but sometimes if it's a straight yes-no decision coming out of code, it'll show you at the bottom. If it's true, we follow this branch. If it's false, we follow this branch. And you can hit the T and F keys just to follow. If you want to follow a branch, false, 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 what happens? Radar will let you track that, which I think is really cool. So why? Why do we do all of this? Like, we showed games and we showed some cool stuff, but there were some really practical reasons to get into reverse engineering. I think the first that I'll mention is that the more people in our Mac, our Apple community that know this, the more knowledge we have, and the more points of view we can get on problems. Reverse engineering is really the ultimate documentation. No matter what the man page says, no matter what the documentation says, the real documentation is how the program actually behaves, and you can find that out through reverse engineering. Sometimes the documentation that you have doesn't exist. Sometimes it's wrong. Sometimes it leaves things out. So yeah, reverse engineering will give you insight, the ultimate insight into what a program's really, really doing. We were talking about this yesterday in one of the security session, and he mentioned Patrick Wardle's tools. Most of those aren't open source, so I don't use them. Here's this guy who used to work for a 3-letter government agency saying, here's all this free stuff loaded onto your computer. Makes me a little nervous. But that would have been really good today, and like, hey, let's reverse engineer this. And I think that's going to be one of my next projects, because like, let's really see what this thing is doing.
Yeah.
Should I be nervous? Should I not be nervous? I don't know. I don't really have source code, so let's dig into this. One example of where reverse engineering came in really handy is when Apple came out with File Vault. There was no enterprise solution for storing keys. Apple in 10.7 didn't have a way to hand you back the license plate recovery keys, so a 2-day bender with GDB and Apple's system preferences and security pane. We saw how the GUI hands you back that license plate style recovery key, and we were able to write a command line tool called CSFDE that mimicked all of that. Another reason I've seen that was really fantastic was when Apple came out with 10.10.3, and they tried to implement all these solutions for the root pipe security bug. They broke their own tool. They broke Create Mobile Account, and some people in the Mac community jumped on top of that. I'm pretty sure Michael Lynn, sitting up here, was one of the main people who sort of used Hopper and went through Create Mobile Account and said, what the heck is going on? Ah, I see, they broke it because of root pipe, and oh, by the way, Mac admins, if you need Create Mobile Account, here's a workaround for it. So people are able to keep their workflows. So there are a lot of reasons to be able to want to dig into code. So how? We just scratched the surface here, right? This could be a week-long class, and we still wouldn't be able to touch everything, but I think my best advice, just like anything, is just tiny steps, and you get used to it over time, and you build up your knowledge over time. Don't expect to be jumping into big programs like, I'm going to reverse engineer Photoshop. Like, that probably shouldn't be your first project, right? Tiny steps, write your own code, and reverse it. That's a great way of learning this. When you mentioned the floating point number storage, I honestly don't know how that's represented. I don't know how that representation works.
Yeah.
So
I
always
just compile.
Yeah.
And I was like, okay, that's a 1.0 copy of that.
Yeah. I write a program that's just like, double equals 5. Reverse engineer it. Okay, that's what 5 looks like. Great, I'm going to use that. Right?
Yep.
I have no idea how those that representation works. So yeah, we want sort of less magic and more understanding. So tiny steps, tiny steps. And hopefully that gets you inspired to go look at this stuff. And I see we're out of time. So we'll be hanging around. We'll be around the rest of the conference. We'll be hanging around for questions. Otherwise, thank you very much for giving us your time and attention.